We are Team 1036 from Colorado State University in Fort Collins, Colorado. We have been instructed by our coach, Dr. Matt Kipper, and have selected problem B, throw the bike or throw the race. Bike throwing is a necessity in getting the edge in a close race. Using a bike throw, the biker thrusts their bike in front of them while simultaneously pushing themselves back, getting as much distance as possible to reach across the finish line. If done correctly and at the right time, a biker can cover the necessary ground to take the lead and win the race. On the contrary, if this move is performed poorly and goes awry, the out of position biker becomes susceptible and can topple off their bike. For a bike throw to work, the biker must extend both their arms and legs forward to cover the most distance as possible. This in turn has a biker become more of a C shape, which results in the person coming off their steep and extending their back, which allows for the farthest distance covered. Shown in the picture, the biker is able to extend the bike farther to get the extra distance to finish the race faster than their counterpart. It is also important to note that in this C shape, the biker becomes more aerodynamic.
The model assumptions for our system are constant velocity with no acceleration at the finish. This means the riders have reached max sprint speed and are not accelerating across the time frame we're evaluating. We also assume that the bikers are starting at the same position and velocity. This allows us to equally compare how the bike throw helps each individual rider. We are also using average weights for the bicycle and the rider themselves, with 15 pounds being the weight of the bicycle and 126 pounds being the weight of the cyclist. We're using an average friction coefficient of 0.004 for a smooth asphalt surface, assuming this is a professional race in a well-maintained environment. And we are also assuming a drag coefficient of 0.6. We are assuming there's no wind and that the drag due to the rider is only calculated over the surface area of their head. This is assuming the rider is in the C-shaped position for the most aerodynamic positioning. We are also assuming that the biker leans back 3 inches during the bike throw, giving them a total advantage of 25.2 inches. We are also assuming constant throw positioning, so their hand position does not change. The only thing changing is their body moves backwards and the bike moves forward during the bike throw. Finally, we are assuming all force due to the bike throw is in the X direction. There is no lift of the bike, so all the advantage of velocity and position is in the X direction. The variables used for our system model are T for the independent variable time, X for the dependent variable distance, V naught for the initial velocity of the bikers as they sprint towards the finish, FD, which is the force of drag due to air resistance, FF, which is force of friction due to the tire on the asphalt, WB, which is the weight of the bike. In our case, it's 15 pounds. WR, the weight of the rider, which is 126 pounds. WSys, which is the weight of the system and is the sum of WB and WR. Mu, which is the rolling coefficient. Rho, which is the density of air. A, which is the area force of drag acts on, and in our case, is just the area of the rider's head. CD, which is the drag coefficient. X back, which is the distance the rider moves backwards during the bike throw. X throw, which is the distance gained from the bike throw. M sys, which is the mass of the system. And G, which is gravity. The equations used to model the system are W system is equal to the weight of the bike plus the weight of the rider. FF is equal to the weight of the system times the rolling friction coefficient. This is the force due to friction. FD, or force due to drag, is equal to 1/2 times the air density times the initial velocity squared times the drag coefficient times the area of the rider's head. The distance gained by the bike throw, X throw, is equal to the weight of the rider divided by the weight of the bike times the distance back that the rider moved. XA is the distance traveled while moving at the initial velocity. XB includes XA as well as the deceleration due to drag and friction while preparing to throw the bike. XC includes the distance traveled during XA and XB, as well as the distance gained by the bike throw, X throw. XD is the distance traveled from XA, B, and C, as well as the deceleration due to drag and friction as the rider crosses the finish line. And finally, msys is the mass of the system, which is the weight of the system divided by gravity.
In problem B, we were tasked with finding the precision and time window needed for a successful bike throw. To do this, we created a model that focuses on the last few feet of a professional bike race. In this model, we looked at the effectiveness of different time bike throws. In this plot, we are showing the distance traveled by a rider against time. The brown line displays a rider with no throw, and all other colors are showing variations of time throws. We have displayed an imaginary finish line at 6 feet to compare the effectiveness of each throw. As we could see from the results, timing is everything for a bike throw to be effective. We saw that throws at 0.03 and 0.05 seconds cross the 6 feet finish line before any other throw, including the no throw. Throws within 2 feet of the finish line in this model would be beaten by better time throws that launched around 3.5 feet from the finish. Showing precision would be key if both riders perform equivalent bike throws. For the bike throw to be effective, the rider should execute the throw within 6 feet of the finish line. If a rider is to throw outside of this range and go into a coast, forces acting on the rider would be too steep and allow the rider who threw within a 6 feet range to pass them before the finish. As far as time being made up, the heavier the rider, the more time that could be made up. The further back a rider can move, the more time that can be made up. The best way to make up this time is to throw exactly the distance you will gain from the finish line.
For when you would want to do a bike throw or not, the only time where a bike throw wouldn't be useful is if you do this too early or too late. This move becomes risky if done too early because the bike becomes out of position and then that elongated C shape can topple over. If the move is done too late, there will be no point in performing it since the race is over and the move will be not used effectively. Asking demi-vollering should tell you the same thing as our results. The bike throw is crucial in a tight race. Without a bike throw, another competitor can couple a couple of feet and possibly take the lead. The key to this trick is all about timing and when the bike is able to get the most bang for its buck. To get that, the biker would want to throw about around 0.02 seconds before the end of the race. If risk is a concern, however, considering this move is only performed at the tail end of a race and only lasts for a fraction of a second, there's little risk in performing this move. It should be added to any toolbox of any great biker. Bikers need this move, so unlike volleying, can volley themselves into first place. Thank you for listening to our presentation, and we'd like to thank SCUDEM for hosting this competition. Have a great day.